Okay, so previously we looked at the integral test and did an example. And to be honest with you, a lot of the techniques that we're going to learn work actually better than the integral test. So there's only a limited set of times that we're going to actually be doing integration to determine whether a series converges or not. But what we do use a lot is one consequence of that. And that is, if we backtrack to integrals, remember we established this fact about integrals, right? That for that type of integral, remember this reciprocal power function has an asymptote at 0. That's why we start past 0 there, and just goes down. And sketch a picture here. We figured out that it wasn't enough, so as long as we're starting past that asymptote, we're looking at something like this, right? And we figured out that really all you had to look at was that power there. If it was greater than 1, the integral converged. If it was less than or equal to 1, it diverged. Well, we just looked at the integral test that said if the function is positive, decreasing, and continuous, well, that reciprocal power function is positive, decreasing, and continuous on the interval starting past that asymptote, so from a to infinity, where a is bigger than 0 there. So this is something that you could do the integral test on, but we already know when it converges or diverges. So what we'd like to do is just port over this fact to p-series, so or what we call p-series. So we're going to call the corresponding series to this function a p-series. And so because of the integral test, we know that a function that's positive, decreasing, continuous, whatever its integral does, the series does. So now we have this new fact that we kind of inherited from integrals. And we'll use p-series a lot, actually. So it's not that integral test is sort of useless. It has its place, and it gets used just not directly. So anytime you're going to be quoting p-series, behind the scenes, the reason we know that is because of the integral test. So the same criteria, that p being greater than 1 tells us it converges, less than or equal to 1 it diverges. So for example, the series 1 over n, you're not going to do the integral test directly. You're just going to use this fact. You're going to say that we know that this is a divergent p-series because p is 1, which is less than or equal to 1. And that's really all you need in your argument. You're letting me know that you understand that's a p-series. You're letting me know you understand that it has to do with that exponent, and that the key is that it be less than or equal to 1 for divergent. Likewise, you could have something like, and it really doesn't matter where we start, right? Anywhere past 0. Typically, when we don't fill anything in here on the sigma, we just mean in general. Really, it doesn't matter where you start for convergence or divergence, but I'll fill it in. So say we go from 1 to infinity of 1 over n square root n. So we have a p-series again. It may be hidden a little bit, but that's just 1 over n to the 3 halves, right? N to the first times n to the half. So that's a convergent p-series. P is 3 halves, which is bigger than 1. So this is nice. It's a very quick argument. Behind the scenes, it really is the integral test, but all you're going to have to do is argue it based on this new fact here of p-series.